Beyond their intrinsic appeal and utility to number theorists, recurrence sequences are important objects in computer science. The question of considerable interest for mathematicians and computer scientists is, can we find a formula that will produce any individual term in a recurrence sequence of numbers without the need for generating all the numbers in the list up to that term? In this lecture, we'll tackle this challenge by discovering the famous Binet formula for the Fibonacci numbers. While named after the French mathematician Jacques Binet, who first derived it in 1843, it appears that this important formula was known to Leonhard Euler and Daniel Bernoulli over 100 years earlier. We'll verify this formula for ourselves by, once again, simply searching for a pattern. Once we derive this formula for ourselves, we'll realize that our method can be generalized and used to find corresponding formulas for all such similar recurrence sequences. The Binet formula will provide us with the insight that while recurrence sequences such as the Fibonacci and Lucca numbers are not geometric progressions, they are in fact a combination of two geometric progressions. Yet again, we see structure. We'll then close this lecture with one of the most famous stories involving recurrence sequences of numbers, the Towers of Hanoi. While today these towers can be viewed as a challenging logic puzzle for mathematicians and computer scientists, as the ancient legend has it, the solution to this conundrum also holds the date at which the world will come to an end. Thus, we'll discover yet another useful piece of information that only comes into focus through the lens of number theory. In the previous lecture, we discovered recurrence sequences, lists of numbers that can be generated using some starting seeds, the first few numbers on our list, and then the fixed rule for generating future numbers. Arithmetic and geometric progressions are very simple examples of recurrence sequences, as are the Fibonacci and Lucca numbers that we saw earlier. A recurrence relation is one in which previous information is used in a systematic manner to generate new information. The concept of recurrence is important and fundamental, and actually an important component in many computer algorithms and languages. And as a result, all computer scientists have studied and make use of recurrent sequences in their programming. Well, we now wonder if there's a so-called closed formula for the Fibonacci numbers, and begin by contrasting the idea of a recurrence definition and a formula. First, I want to name the Fibonacci numbers, which is something we haven't done yet. We've just listed them. Remember, they begin 1, 1, 2, 3, 5, 8, and so forth. But now I want to give them names in terms of their position in the list. So we name them by using the symbol F with a subscript n. And this is read either F sub n for subscript n or Fn. Sometimes it's abbreviated. And what it means is the number n is denoting the location on the sequence at which we're at. So, for example, F1 would denote the first Fibonacci number, or the Fibonacci number in the first spot, which would equal 1. F sub 2 would be the next one, the second Fibonacci number, which remember is also 1. F sub 3 would indicate the third Fibonacci number, which is 2. F sub 4 equals 3, F sub 5 equals 5, F sub 6 equals 8, and F sub 7, which means the seventh Fibonacci number on our list, would be 13, and so on. So I'm going to use F sub n to denote the nth Fibonacci number, or a generic Fibonacci number. Well, this notation actually allows us to precisely define the recurrence rule that we've seen before, and it would be said this way. F sub n plus 1 equals F sub n plus F sub n minus 1, and this holds for all natural numbers n greater than or equal to 2. Now, what does this mean? What it means is, if you want to find the n plus first Fibonacci number, what you do is add the two previous ones. Well, if this is the n plus first Fibonacci number, what's the one right before it? It would be the nth Fibonacci number, and the one before that would be the n minus 1th Fibonacci number. So fn plus fn minus 1, if we add those two, we get fn plus 1. And that's what that formula means. However handy this notation might be, one disadvantage in defining the Fibonacci numbers as a recurrence sequence is that if we wish to find the value of a far-off one, say, for example, the 1000th Fibonacci number, which would be f sub 1000, we'd be required to compute all the previous Fibonacci numbers in succession and work our way up to the 1000th one, because the rule is recurrence in the sense that we need the previous ones to get the next one. So we need to find all of them to get the 1000th one, all of them up to 1000. Ideally, we would like a so-called closed formula. In other words, a generic formula in which we can literally just plug in the number 1000 and produce the 1000th Fibonacci number without actually computing all the previous ones. One of the important features of many recurrence sequences in general is that such closed formulas can be derived, and we'll illustrate this process with the famous Fibonacci numbers themselves. We recall that in our attempt to express the golden ratio, which we denote by the Greek letter phi, in a more familiar form rather than as a continued fraction of ones, we saw that phi was one of the solutions to a particular quadratic equation, in particular x squared equals x plus 1. Now, using the quadratic formula, we found that the two solutions to this equation are 1 plus the square root of 5 divided by 2, and the other solution, 1 minus the square root of 5 divided by 2. Well, because the number phi, the golden ratio, is a positive number, we found that phi equals the positive one, 1 plus square root of 5 over 2. But now we're going to actually talk about the other solution as well, and so we'll give that a name. We'll use the Greek letter tau to denote that solution. And so in other words, tau will equal 1 minus the square root of 5 over 2. Now, here's an important insight. Since both phi and tau are solutions to the original quadratic equation, we see that if we plug those values in, they will satisfy the equation. So in particular, we see that phi squared equals phi plus 1, and similarly, tau squared must equal tau plus 1. Now, these important equations hold the key to finding a formula for the Fibonacci numbers. And I want us to see how we can use these identities to actually find the formula. Well, we can actually use the formula phi squared equals phi plus 1 to simplify higher powers of phi. And so I want us to think about this together. Let's consider phi cubed, which means phi times phi times phi. Well, phi cubed is nothing more than phi multiplied by phi squared. Now, phi squared, we know from the previous equation, is the same thing as phi plus 1. So instead of having a phi squared, I can replace it by its twin, phi plus 1. I have the plus 1 now, but notice no square. So I've reduced the complexity. So let's come back to phi cubed. Phi cubed equals phi times phi squared. And phi squared, in turn, is phi plus 1. So phi cubed equals phi times phi plus 1. And if I distribute, I see that phi cubed equals phi squared plus phi. Well, that's all well and good, but I have a phi squared, which again I can simplify and reduce to just phi plus 1. So I'd see phi plus 1 plus that extra phi, or 2 phi plus 1. And so in conclusion, we see that phi cubed equals 2 phi plus 1. Lots of algebra, but if we work through it carefully, we see this identity holds. Well, let's see if we can actually uncover a familiar pattern of numbers as we compute these higher and higher powers of phi. I'll just do a couple more just to illustrate the idea. So we can apply the exact same technique to find a simple way of writing phi to the 4th power. How? We proceed as we just did. phi to the fourth equals phi times phi cubed. Phi cubed, we just discovered, was 2 phi plus 1. So now I have phi times 2 phi plus 1. When I distribute that phi, I see 2 phi squared plus phi. Well, the phi squared, reverting back to our very first formula, is the same thing as phi plus 1. So I now see 2 times the quantity, phi plus 1, plus an extra phi. So I have 2 phi plus phi is 3 phi, and then I have plus 2. So now I see that phi to the fourth equals 3 phi plus 2. Do you notice anything about these numbers in front of the phi and the number that we're adding? Well, again, might not be clear. Let's look for the formula for phi to the fifth. We continue. Phi to the fifth equals phi times phi to the fourth. Phi to the fourth we just found to be 3 phi plus 2. So I have phi times 3 phi plus 2. When I distribute, I see 3 phi squared plus 2 phi. Well, again, the phi squared is nothing more than phi plus 1. So I see 3 times phi plus 1 plus 2 phi. 3 phi plus 2 phi is 5 phi, and then I have that plus 3 at the end. Notice anything with respect to 5 and 3? Well, finally, let's look at phi to the sixth. Let's just do one more. I promise, this is it. Well, phi to the sixth equals phi times phi to the fifth. I hope you see the pattern forming. That's phi times our previous answer, which is 5 phi plus 3. When I distribute, I get 5 phi squared plus 3 phi. Again, I can see a phi squared. That's just phi plus 1, all multiplied by 5. So 5 phi plus 3 phi is 8 phi, and then I have a plus 5. And now, hopefully, a pattern is beginning to emerge. If we collect all our findings, we'll see in a list, phi squared equals phi plus 1. Phi cubed equals 2 phi plus 1. Phi to the fourth equals 3 phi plus 2. Phi to the fifth equals 5 phi plus 3. Phi to the sixth equals 8 phi plus 5. Now, what do you see in that list? Well, notice that we see Fibonacci numbers. If you look down in the columns, you just see the Fibonacci numbers listed in order. And if you look across any particular row, you see 2 consecutive Fibonacci numbers, a big one followed by the smaller one that comes before it. Well, we see the Fibonacci numbers appearing. In fact, we can continue this process indefinitely and thus conclude that we have a general formula for any natural number n. And so here's the formula that we're seeing within the pattern. If I look at the nth power of phi, or phi to the n, that will equal the nth Fibonacci number times phi plus the Fibonacci number before that. Or said mathematically, phi to the n equals phi sub n phi to the n equals f sub n times phi plus f sub n minus 1. Notice that's exactly what we just said. The nth power of phi equals the nth Fibonacci number times phi plus the Fibonacci number that comes right before. Well, by the identical reasoning, since tau is also a solution of x squared equals x plus 1, we can show that a corresponding formula holds for tau. In other words, for any natural numbers n, we also have that tau to the n equals the nth Fibonacci number times tau plus the Fibonacci number that comes before. Or said formulaic, tau to the n equals f sub n times tau plus f sub n minus 1. Well, if we take these two equations and now subtract the formulas, what do we see? Well, I see phi to the n minus tau to the n on the left-hand side. And on the right-hand side, notice that the f n minus 1s cancel when I subtract. And so all I'm left with on the right-hand side is the nth Fibonacci number times the quantity phi minus tau. Well, this is fantastic because we can solve this for fn, or the nth Fibonacci number. All we have to do is divide both sides by phi minus tau. And I see the formula fn equals phi to the n minus tau to the n, all divided by phi minus tau. Now we have a formula for phi to the n. Now we can simplify that a little bit more because we can figure out what phi minus tau is. What is it? Well, remember that phi is 1 plus square root of 5 all over 2. Now we're going to subtract tau, which is 1 minus square root of 5 over 2. And so when we break this up, we see 1/2 plus square root of 5 over 2 minus 1/2 minus square root of 5 over 2. And so the 1/2s cancel, and I'm left with square root of 5 over 2 minus negative square root of 5 over 2, which means square root of 5 over 2 plus square root of 5 over 2, which equals just the square root of 5. And thus we've derived a closed formula for the nth Fibonacci number in general. F sub n equals phi to the n minus tau to the n, all divided by the square root of 5. Or in other words, the nth Fibonacci number equals phi raised to the nth power minus tau raised to the nth power, all divided by the square root of 5. Well, this elegant formula today is known as the Binet formula, named after the 19th century French mathematician Jacques Binet. And by the way, we can now find the 1,000th Fibonacci number. How do we do it? We just let n equal 1,000. So the 1,000th Fibonacci number equals phi to the 1,000 power minus tau to the 1,000 power, all divided by square root of 5. Now, I don't know about you, but I can't do that in my head. But a computer can simplify that, and it would produce a 209-digit Fibonacci number that begins 4, 3, 4, 6, 6, 5, 5, and so forth. 209 digits. The important thing here is that we found this number without ever computing any of the previous Fibonacci numbers before it. This is the power of a closed formula. There was no need to work our way up. We landed right there. So absolutely powerful and beautiful identity. Let's now recall from the previous lecture that we found that the Fibonacci sequence is not a geometric progression, since the ratio of consecutive terms, in fact, is not constant. We did see that those ratios are, in fact, converging on a particular value. The value of the ratio that the ratios are actually approaching, we saw, was the golden ratio, 1 plus square root of 5 over 2, also known as phi. Well, using Binet's formula, we now discovered that the Fibonacci numbers are, in fact, the difference of two geometric progressions. Do you see it? Because we have the phi to the n over square root of 5. That's a geometric progression, multiplying by phi each time. And then we subtract off tau to the n divided by square root of 5, where again, a geometric progression we multiply by tau each time. So it's absolutely wonderful that even though we see that the Fibonacci numbers are not, in fact, examples of a geometric progression, we see that, in fact, since those ratios of terms were converging to something else was happening. It's actually the difference of two geometric progressions. Again, we see structure. Now, we could actually apply the previous analysis exactly with the Lucas sequence, and we derive a different closed formula, and that closed formula would be for all natural numbers n greater than or equal to 2, the nth Lucas number would be equal to phi to the n minus 1 power plus tau to the n minus 1 power. And notice it's a similar looking formula. It involves both the phi and the tau. In this case, we're adding, and we have different exponents. In fact, using the same ideas, the terms of any such recurrent sequence can be expressed as, in fact, a closed formula. Well, I want to close this lecture on recurrence with the legend of the Towers of Hanoi. The Towers of Hanoi was a logic puzzle that was marketed in 1883 by a so-called Professor Claus. However, the name Professor Claus is in fact an anagram of its true inventor, Professor Lucas. So maybe he invented this game to subsidize his retirement. I don't know. But anyway, he was marketing this thing, which is kind of neat. Well, the Towers of Hanoi puzzle consists of 3 pegs, and I actually have one here. So this is what it looks like. Usually they're made out of wood. It consists of 3 pegs and a collection of punctured discs. And you can see these punctured discs here. So they have holes in them, so they fit over the pegs. But the pegs are, the discs are of different sizes. Okay, and so the puzzle begins with all the pegs disks rather, on one peg, and in descending order. So we go from smallest to, we go from the largest on the bottom up to the smallest on the top. Now the object is to transfer all the disks to another peg so that they end up residing on this new peg in the original descending order. So what we want to do is we start this way and we want to end, say, with all of them sitting here. But there are some rules, because otherwise the solution would be literally what I'm doing right now. So there are some rules, and here are the rules. First of all, only one disk can be moved at a time. So only one disk can be moved at a time. And at no time can a larger disk be placed on top of a smaller disk. So while I could take this disk and put it here, I would not be permitted to put it here. That's against the rules because I have a larger one on top of a smaller one. That's not allowed. So that, in fact, is against the rules. Well, the challenge is to find a method for moving the disks and to determine the smallest number of moves required to solve the puzzle, to move all of them. Well, this is truly a towering recurrence, as we're about to see. Well, let's suppose that in general we have n disks to be moved for some natural number n. We begin by observing that to move the largest, very bottom disk, we must first remove all the other n-1 smaller disks. Now, once we remove those n-1 disks to a new peg, then we can actually free up that last biggest disk to be moved onto the empty peg. However, now we must remove all the previous disks and move them back on top of the largest one. Let's now give this a name, the number of steps involved in solving this a name. Let's write h sub n for the number of moves required to transfer n disks. So in other words, h sub 1 would equal the number of moves required to move one disk and so forth. Well, we now wonder if we can find a recurrence rule that actually generates the sequence of numbers h sub n. Well, let's see if we can find a pattern by coming back to the puzzle. Now, instead of performing the puzzle with all these disks, let me just start by looking at 3 disks first. So how many moves are required which would be equal to h sub 3? I have 3 disks, n would be 3 here. H sub 3 would be the minimum number of moves. Well, if we try it, we see what happens. I'll move this smallest one to here, then I'll move the middle one to this empty one. Now to move this largest one, I can't put it on top of either of these, so I'll take the little one and put it on top of this, which is allowed because the small is on top of the medium. Then the large is now freed up to be moved to here, and then now I can't pick these both up, but I can now take the little one and put it on this empty one, take the medium one, put it back on the big one, and the little one gets back on top. So how many moves was that? I'll do it a little bit quicker now, and now all we'll do is just count. So if we count, we see 1, 2, 3, 4, 5, 6, 7. So 7 moves are required, and in fact that's the shortest, the fewest number of moves required to do 3. Let's now consider 4. So I'm going to add on a bigger one. Now to do 4, let's just think about it. I first have to move all of these off, then move this, and then move them all back on. So let's see what happens if we do this. I'm going to count right now. So here we go live. 1, 2, 3, 4, 5, 6, 7. So there was the 7 to move it. Now this is free, so I picked this up and I'm going to put it here. So I had 7, now I just moved it. That's an 8th move, and now we've got to continue. So an 8th move, 9, 10, 11, 12, 13, 14, 15. Voila, I did it. Amazing as it may seem, I was able to do this, which means that if we look at n equals 4, the answer is 15. H sub 4 is 15. Now let's think about what's going on here. In view of this disk moving process, h sub n actually must equal h sub n minus 1. First move the top n minus 1 disks. Then you move that biggest disk, which is another move, so plus 1 move. And then you got to move all these from where they are back on top. So that's another hn minus 1. So we see that hn has to equal hn minus 1 plus 1 plus hn minus 1 again. In other words, we have a recurrence rule. Hn equals 2hn minus 1 plus 1. Remember that moving that bottom disk is where we get the plus 1. Well, so the number of moves required for 4 disks, if we use this formula, equals 2 times the number of moves required to move 3, which we saw was 7. So 2 times 7 plus 1, which is 15, which is what we got when we worked it out for ourselves. So this is actually good. Now, the question is, can we find a closed formula by looking at our sequence of h's? So we have a recurrence definition for h. Now we want to see if we can find a closed formula for h sub n. Well, let's look at the numbers. 1, so if we just had one disk, it's easy, just literally move it, and so 1. Then the next count would be 3. The next count is 7, which is what we saw, and then 15. Now, do we notice anything about 1, 3, 7, 15? Again, we're always looking for a pattern. Well, in this case, we notice that each number is actually 1 less than a power of 2. Let's check it out for ourselves. Notice that 1 equals 2 minus 1. 3 equals 4 minus 1, which is 2 squared minus 1. 7 equals 8 minus 1, which is 2 cubed minus 1. And even 15 is equal to 16 minus 1, which is 2 to the 4th minus 1. In general, it's actually possible to prove that h sub n, the number of moves required with n disks, is equal to 2 to the n minus 1, which gives our simple closed formula for the number of disk moves required if we have n disks. Well, for our model with 7 disks, you might say, gee, how come, you might be a little bit disappointed that I'm doing it only with 4, and I didn't revert back to the original one, which notice has 3 more, so it actually has a total of 7 disks. Gee, how come you didn't do it with 7 disks? Well, we can now see how many moves that would take. It would equal 2 to the 7th power minus 1. The closed formula gives it to us immediately, which is 128 minus 1, or 127 moves. So if you want to solve this puzzle, you'll need a little bit of time because it's going to require 127 moves. Well, now using this formula, we can actually determine the end of the world. There's a legend that a certain group of monks had a particularly impressive edition of this puzzle consisting of 64 gold discs and 3 diamond pegs. And they were able to move, the monks were able to move these discs at a pretty alarming rate, 1 disc per second. Now the legend is that the world would end once the monks completed their mission. We can now use the closed formula we just found to predict when the world will end, according to legend. The number of moves required to solve this puzzle with 64 discs equals 2 to the 64 minus 1. You see the power of the closed formula. Well, given that the monks move the discs at a rate of 1 disc per second, this number of moves would take 583,344,214,028 years, and thus that many years for the world to end. So you might think about putting a hold on your mail. Anyway, what if we had 4 pegs? So let's go back to the puzzle and add an extra degree of freedom, namely add an extra peg here, which I don't have at our disposal, so let's just use our imagination and see what would happen if we had 4 pegs. Well, if we had a 4th peg, then in fact, instead of taking 7 steps, we would actually require fewer. Let's try it with just 3. We used 7 before, but now what I'll do is I'll take this little one and put it on the invisible 4th peg. And then I can just move this to here, move the big one to here, put the medium back to here, and then put this back to here. How many moves was that? Well, that was actually only 5 moves. So we actually, with that extra peg, we'd have an extra degree of freedom, and so therefore we'd need fewer moves, certainly less than 7. Well, it turns out that the optimal strategy and the optimal solution for the towers of Hanoi with 4 pegs actually remains an open question. So in fact, you can see just adding 1 peg leads us from the world that we understand and drives us into the world of the unknown. Open questions abound. The importance here is that we see that recurrent sequences have a particularly nice form, and certain recurrent sequences can actually lead to a closed formula, a way of generating a far, far out term without going through the steps of finding all the terms before. Amazing number theoretic structure within recurrent sequences.